So if we draw this plane out, here we have our second joint, which is right here, and this is our second joint, so it means it corresponding to this line, okay? So which is the second link, and right here we have the third joint, which is right here, so that is the third joint. And then from the third joint to the spherical wrist center, so we have the third link. Okay, and here we assume this is OC, which is the spherical wrist center. So now this whole thing, we draw it right here, and it is corresponding to this plane. Okay, and assume that, okay, so this line is parallel to the ground. Okay, so this line is parallel to the ground. So actually, all of these is a little bit above the horizontal line. Okay. So assume this is the horizontal line, and which is parallel to the ground, right? And which is corresponding to this line, okay? This line. And then if we draw a line that is along the second link, okay, which is along the second link, so we have this line, and so this angle, which is between the second link and the ground, so here we have theta 2. And again, theta 3, that is the angle if we draw a line that is along the length 3 and between this line and this line, so we have theta 3, because theta 3 is the angle compared to the second link. Okay, so we also know that the link 2 has the length A2 and the link 3 has the length A3. Okay, and okay, so seems like this is the projection on this plane. Okay, and so then that is the same as this one. So this is how this side view comes from. And then we can do the analysis. So if we want to calculate theta 2 and theta 3, so let me start with theta 3. So if we want to calculate the theta 3, and seems like the theta 3 is, it has the same line of this angle, okay? So this theta 3 plus this angle equals to pi, okay? Equals to pi. So if we want to calculate theta 3, and we probably can calculate from this angle, which is pi minus theta 3. And I also would like to draw a line connecting, and here is OC, which is the spherical wrist center, and this is the center of joint 2. Okay, so if we draw a line right here, and this line corresponding to, in the 3D, it corresponding to the, here we draw a line from the center to OC. Okay, and then we can use this triangle to quickly analyze this angle. Let me call it alpha. Okay, so we know that if we know this alpha, cosine alpha equals to, if we take a look at this triangle, equals to this side, which is A2 square plus A3 square minus this, let me call it B, minus B square. This is triangle rule, right? And over 2A2, A3. Okay. So this is always true for whatever triangle, okay? So cosine alpha equals to this A2 square plus A3 square minus this B square, and over 2 times A2, A3. Okay, so then it means the cosine theta 3 equals to minus, because alpha equals to pi minus theta 3, right? And so cosine theta 3 equals to cosine pi minus alpha, so that is negative cosine alpha. So this thing equals to B square minus A2 square minus A3 square over 2 times A2, A3. And what is this B? And the B is from the joint connecting to the spherical wrist center. So let me take a look at what is this B. Okay, so from here to here, this is B. So the B actually is, okay, so if we draw a line, so here, this thing, this length is actually equals to this length, right? Because this thing and this thing is parallel. And from the spherical wrist center to here, okay? So this is S. In the figure, we called it S. And this is S. So it means this B square equals to this length, which is R square plus S square. S means from the spherical wrist center to the level, to the height of the second joint. Okay, so that is R. R from this figure, it is actually equals to this line. So R square equals to C square plus YC square, right? Because R is the projection on the ground, okay? So then that in this case there is no offset. Remember that we talk about the different configurations of this elbow manipulator, and the first case, which is the simplest case, that is exactly the same as this drawing, that we do not have the offset of the shoulder. Okay, and then we also talk about some more general cases that are left arm configuration and right arm configuration. It means that right here we have an offset, okay, right here we have an offset, so means then we have a D. Okay, so from the previous analysis, this D, if we want to write one equation to consider all the cases, then we need to minus this D square, so that we're able to calculate this R square, okay? And this D square, if in this case, if D is 0, means there's no offset, and then that R equals to XC square plus YC square. If it's right arm or left arm configuration, and there is a D, and then this R will be equals to SC square plus YC square and minus this D square. Okay, so this is a general format of how to calculate the R square. And then how about S? S is from the height of the spherical wrist center to the height of the second joint, which is right here, right? So this S actually equals to the height of the total height of the spherical wrist center, which we already know, okay? So again, this OC, it has the coordinates of XC, YC, and ZC, which we already know that, right? Okay, so we already know that, so that is, this height will be ZC, okay? It is ZC. And then we know that from the ground to the height of the second joint, this distance is equals to the geometry, which is the length of the first link. So that is D1. Okay, so then the S is pretty simple to be calculated. It just equals to the total height of the spherical wrist center, which is ZC, minus the height of the second wrist and the second joint, so which is the geometry, which is the length of the first link. So that is D1. So S equals to ZC minus D1. Okay, so it means that we can quickly calculate our theta 3. So our theta 3 is actually equals to this R square. We already know that this R square equals to A2 square plus this R square. Okay, sorry. This R square, we already know that this is XC square plus YC square minus D square, okay? And this XC, this S square equals to, the S equals to ZC minus D1, so the S square equals to ZC minus D1 square, okay? So then in total, we're gonna have this cosine theta equals to this term. Okay, so then you can quickly calculate the theta 3 by this cosine, so it's arc this whole terms. So again, this A2, A3, XC, YC, and ZC, they're the coordinates of the spherical wrist center. And A2, A3, and D1, D is the offset of the shoulder, and these are the geometry, okay? So let me mark as a small dash, okay? So these are the geometry. And these three are the coordinates of the spherical wrist center. So then we can quickly calculate theta 3, and because they're all known. Okay, so once we know theta 3, and then we can start to calculate theta 2. Okay, so theta 2 is this angle. Okay, so if we want to calculate this angle, and we will need to this clear figure that if we want to calculate the theta 3, and theta 3 equals to this big angle minus this angle, right? This angle. Okay, so if we call the thing is beta and the thing is gamma, so theta 2 equals to beta minus gamma. And what is beta? And beta, again, we already know this length, right? This length is S. Okay, so beta, and this length is R. So beta, from the analysis of theta 3, we can quickly calculate beta. So beta is arc tangent R and S. Okay, and how about the gamma? The gamma is the small angle. If we want to calculate the small angle, again, we go back to use this triangle. Okay, so if we want to calculate this small gamma, and again, what is cosine gamma? Cosine gamma. Okay, cosine gamma equals to b squared plus a2 squared minus this length, that is a3 squared, over 2b. What is S? S equals to c minus d1. Okay, so then the b actually, okay, sorry, here b equals to r squared plus s squared, okay, and r squared equals to xc squared plus yc squared minus d squared. Okay, so we plug in these two, and then we're able to calculate this b. Okay, so this is b squared, right? Okay, so then plug in this b squared, so we're able to calculate cosine gamma, and means we're also able to calculate tangent gamma as well if we want to use the unified consistent tangent shape format. Okay, so then it means here we can calculate the angle, which is this beta, and we can also calculate this gamma, so we can quickly calculate theta 2. So theta 2 equals 2, and this is beta, and this is gamma, so that we can do the quick calculation. Okay, so that is the calculation of the first three joint variables, which is theta 1, theta 2, and theta 3. Okay, so then here we take a look at this Puma robot. This Puma robot is an example of the manipulator with offset. Okay, so it means we have the offset D. Okay, so this is D. And this is a left arm set configuration, and this is a right arm configuration. Okay, just use your own shoulder. Use your shoulder to think about, okay, so this is going to be your left arm, right? And your left arm, your left elbow, and this is your right arm. Okay, and this is your left arm, and now your elbow is down. Okay, so for example, just try, please try your own arm and see if you can do that. Okay, of course we can do that. And so again, this part is kind of the shoulder, the length of the shoulder. Okay, so which is D. So actually from these analysis, we can see that, I mean, although we're able to calculate these three joint variables, theta 1, theta 2, and theta 3, actually maybe there is not a unique solution. There could be two solutions for the spherical wrist. Okay, so one is up and one is down for both right and left and right configuration. So here, this is an example of R, which is theta 1, theta 2, and theta 3. Okay, just the Puma robot, we can see that is a good example to show a RRR manipulator structure. And then once we want to add spherical wrist, and then we can quickly add the spherical wrist right here, and which is corresponding to the OC, right? OC. So now let's try to do more practice. Let's try another configuration, which is a RRP. And still at the end, we add a spherical wrist. So still this is the case 1, means that we have a spherical wrist. Once we have this spherical wrist, we can use this method to do the analysis. Okay, so now we have the spherical wrist center right here. Instead of 3 revolute joints, now we have a prismatic joint here. Okay, so if we want to do the calculation of all the joint variables in this configuration, so what are those 3 variables? In this case, instead of theta 1, theta 2, and theta 3, now we need to calculate theta 1, theta 2, and D3. Okay, so then again, we are practicing the geometry method to calculate the first 3 joint variables other than the spherical wrist. Okay, so now to do this example, we start to do theta 1 and as what we did last time for the RRR. Okay, so to calculate theta 1, again, we need to take a look at the top view. Okay, so we take a look at the top view, and so here it seems like the theta 1 is the same as the RRR configuration. So here we have the theta 1, and this is the spherical wrist center, which is the OC, and which means OC has the coordinates XC, YC, and ZC, and this is the spherical wrist center projected to the X0, Y0 plane. And so it means that right here we have the XC, and on the Y0 axis we have YC. Okay, so to calculate this theta 1, and that is pretty easy because this is the triangle, and right here we have YC, and here we have XC, and this is perpendicular. Okay, so if we draw that, and here I have my X0, here I have my Y0, and this is the OC projected to the X0, Y0 plane. And so if we use this triangle, and this is XC, and this is YC, and this is my theta 1, so my theta 1 equals to arc tangent XC and YC. Or if it is opposite direction, or theta 1 equals to this angle plus pi, okay, plus pi, which is the other side. Okay, and then we start to use the same method to do the analysis of theta 2 and D3. In this case, it's theta 2 and D3. Again, we need to use this plane, and which is the side view, to do the analysis. Okay, so if we use this plane, and then again right here it means this D1 means the height of the center of the second joint, so it means this length is D1, and this is up above the horizontal line because this line is parallel to the horizontal, which is parallel. Okay, so what is theta 2? And now, actually, for this case, it seems like easier because this whole thing is the same axis, which means they're the same line, and there is no theta 3, right? Instead, they're on the same angle, okay? So it means from the center of the spherical, the center of the second joint to the spherical wrist center, there is only one line, and this length is D3, okay? And then the D3, if we draw the side view, okay, so here we have the center of the second joint, and then we have this D3, and D3 goes to the spherical wrist center, which is OC, and right here we have the R, and again R, the length of this R equals to this length, and which is square of XC square plus YC square. Okay, and this length equals to this length, which is the difference between the height of the spherical wrist center and height of the height of the second joint. Okay, so this is D1 and this whole total length is ZC. Okay, and then we can start to do the analysis. So it seems like D3 is pretty simple, right? D3, what is D3? D3, if we take a look at this triangle and this is perpendicular, so D3 equals to square R square plus this is S. In the previous analysis, we used this as S, so now we use the same S. So this is in this square, in this triangle, and D3 equals to square S square plus R square. Okay, and what is R and what is S? R square equals to, R is this one, right? Which is, this is R. Okay, so equals to XC square plus YC square. And what is S? And S equals to ZC minus D1. Okay, so then D3 can be directly calculated. And how about theta 2? So now we have theta 2 is right here, and theta 2 is, we can just directly use this triangle to do that. So theta 2 equals to arc tangent RS. Okay, and if we take a look at this configuration, and it seems like in this example, it shows that x2 is pointing to this direction instead of this small. Okay, so it seems like theta 2 point to this direction, so it's going to be, this is theta 2, and so this is theta 2, okay? And so this is going to be this theta 2, the small angle plus pi over 2, okay? So this is because in this example, it already gave us the theta 2, and so that is the small angle plus this pi over 2. Okay, so that is pretty simple, right? So again, this example shows another configuration of the base 3 joint variables. And the RRR and this RRP, they're all in, for the first case means we have a spherical wrist center over here. Okay, so then the next step, let's see how we're gonna add the spherical wrist center at this OC. So now, if we want to add a spherical wrist, means we need to add 3 joints. Once we add the spherical wrist, we add 3 joints, which means they're theta 3, theta 4, theta 5, and theta 6 as the wrist. Okay, so that we can achieve these 3 rotation axes. Okay, so it's like we're using the Euler angles. And then the question is how we're going to find these 3 joint variables. Again, they are joint variables. Again, for inverse kinematics, we are looking for the joint variables for the target desired position and orientation of the end effector. Okay, so means we already know the final homogeneous transformation H, so that we want to find with this known H, we go back to find, in this case, 6 joint variables, right? 6 QI. QI means it can be DI for prismatic joint or theta I for revolute joint, okay? So now what we're doing so far is just to calculate the six joint variables from this H. So now after we calculated the 3 and the first 3 joint variables, now we go to the spherical wrist. Okay, so as we talk about in the kinematic decoupling that if we can calculate R30, we can then use the decoupling to calculate R63. Okay, and now, because we already know the H, which is the final homogeneous transformation matrix, it means that we already know the R, okay? So we know the R because R is the first 9 elements in the H matrix, okay? And this matrix should be a real number. So this R11, R12, they're all real numbers, which is given. Okay? Okay, so we know these real numbers. And how about R30? Okay, from the forward kinematics. Forward kinematics, if we want to calculate R30 or R60 or R63, so all of these we can calculate it from the DH convention, and which means this table, and then that is the forward kinematics, and then we know what is the format, which is the function of all the joint variables, right? The function of joint variables. Okay, and this is our R30, and means we can quickly take a look at this drawing, and we can do the analysis of AI, alpha I, di, and theta I, which we already did a lot of examples. So now we directly gave this table, and I believe you can quickly come up with these 3 rows from this configuration. Okay, so now once we have these 4 parameters for each transformation, and then we can come up with this R30. Okay, so R30 equals to A1, A2, and A3. Okay, so that we are able to finally come up with this format. And how about R63? R63 by definition equals to A4 times A5 times A6, and again for A4, A5, and A6, and this is from the spherical wrist, which we did it in the forward kinematics example. If you cannot remember the details, please go back to the lecture slides and take a look at this DH convention as well as the final R36, which we did in, I guess it was example 3 in the forward kinematics. Okay, spherical wrist. And now we directly use the result from that example, so we have this matrix of R63. Okay, so now we have the next step. From the kinematic decoupling, we know that if we have a spherical wrist, and then we can use this calculation, and this calculation to calculate R63. Okay, and this R is the final rotation we want, and which means the real matrix, number matrix, right? And which in the previous slide, and this is given as R11, R12, R13, and this is R21, R22, R23, and this is R31, R32, and R33. And this R30 and this R30, and which is from here, right? This R30. Okay. And also from these C1, and it means cosine theta 1, and C2 and C3. For this configuration, this is the RRR example we did at the first one. So it means these theta 1, theta 2, and theta 3, we're able to calculate them, right? We're able to calculate them from the geometry, Okay. So now let's do something interesting. Okay, so from this R63, from the forward kinematics analysis, which is right here, and we already know the 9 elements of this R63 matrix. Okay, so the first term is C4 times C5 times C6 minus S4 times S6. It means cosine theta 4, and this is cosine theta 5, cosine theta 6. And again, this is sine theta 4, and this is sine theta 6. Okay, so the first term from the DH convention calculation, and we have this term, and so which is a function of and C1, C2, function of theta 4, theta 5, and theta 6. And in total, we have these 9 elements. And also from this equation, and we also be able to calculate this matrix, multiply this matrix, which is a real number matrix. So it means that by using this matrix equation, we're going to have 9 equations and 3 unknowns. And these 3 unknowns are theta 4, theta 5, and theta 6. So now what we are doing is just to solve these 9 equations so that we can solve these theta 4, theta 5, and theta 6. Okay, so in this example, what we are doing is we just take a look at which one is simple in this 9 equations, which ones are simple so that we can choose to calculate these 3 unknowns. And seems like here, okay, and this is pretty simple, right? Because we only have C4 and C5, and it seems like from here we can directly calculate this theta 5. So we will do that. Okay, so then we use these 3 elements, and these 3 elements equals to these 3 elements in this multiplication result. So from this multiplication result, and this is a real number matrix, and this is the function of theta 1, theta 2, and theta 3, which we just did it already. And now we're able to come up with 3 equations. These 3 equations are these 3 elements equals to each other from this matrix and from this matrix. And so on the right hand side, they are either real numbers or the joint variables of theta 1, theta 2, and theta 3. And on this side, they are the unknowns we're trying to solve, which is theta 4, theta 5, and theta 6. In this case, we're just calculating theta 4 and theta 5. So this is the first step. But anyway, what we're doing here is just to solve these 9, because this is a 3 times 3 matrix, so we're calculating these 9 equations so that we can solve for these 3 elements from this real number, from real number R matrix, and the joint variable theta 1, theta 2, and theta 3. Okay, so that's it. So now let me just skip these calculation procedure, because I mean for these you can quickly use MATLAB to solve those, and I will just skip this calculation part. So finally we will be able to calculate this theta 5. Okay, so theta 5 equals to this whole thing, and this is theta 1 sine theta 1, and this R13, and it's a real number, so we can calculate theta 5. And we go back to calculate theta 4, and this is over theta 4, and this is over theta 6 from the calculation. Okay, because we're solving 9 equations so that we can calculate the theta 3, theta 4, and theta 5. Okay. Oh, sorry. Theta 4, theta 5, and theta 6. Okay. So we're all set. We're all set. So until here, what we're doing is we're dealing with the first case that the manipulator we're trying to solve is having a spherical wrist. Once we have a spherical wrist, normally at least we have 6 joints, because we need to have a base of the manipulator, and normally it has 3 joints. And then at the end of the manipulator base, and we add a spherical wrist, so that in total we have a pretty complicated robotic manipulator. So if this is our case as the manipulator, and as a summary, we can calculate the 6 variables for only this case of manipulator. And this is a summary of the RRR plus a spherical wrist. spherical wrist. Okay, so the first 3 joints we calculated from the geometry, and the rest of 3 we're calculating from the 9 equations and 3 unknowns. Okay, so again, what we're doing here is to calculate the closed form solution. So why we do this complicated calculation rather than just solve the 12 nonlinear equation is because we're trying to solve the closed form solutions of the 6 joint variables, because we want to do real-time control. We don't want to, the calculation takes like 1 hour to finally give these results. It won't work for real-time control. So that's why we need the closed form calculation. Okay, so now I'm going to stop here for the first case, and which means we have a spherical wrist, no matter what is the base. And if you have another type of configuration, for example, the second example we did in today's class, and we did the RRP as well, in that case, the whole calculation could be a little bit different, but the idea, the logic is the same. Okay, and so next time we'll talk about a second configuration, which means there is no spherical wrist, and then we're gonna do something different.